Hi there, Andrew Dunkley here, the host of Space Nuts. Glad you could join us again for a brand new episode. And coming up on this particular episode, 369, we'll be looking at solar winds. We've known about them for a long time, but we haven't really been sure about what creates them. Well, now they think they know. And spots on Neptune. Yes, it's got acne. We'll also be answering audience questions about photons, gas clouds, and living on Mars versus living on Venus. That's all to come on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me as always is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you doing this morning?
I am quite well, considering that I played a very horrible game of golf last weekend, and just to finish me off, I walked out into the car park and I had a flat tyre. Doesn't get much worse than that.
Well, you could have had argy-bargy along the way. Who knows?
No, actually, it can get worse because I changed the tyre and found that there was a different wheel. Wasn't the same matching wheel as the one that came off, and different set of nuts, and one of them was the wrong size. So,
Yeah, that's
a little bit more salt into the wound there.
It's a new car as well, isn't it?
It is, yeah. But they don't give you spare tyres anymore in certain models, and so I had to request a spare because where I live, you can get stranded a long way from anywhere, and you don't want one of those limited distance sort of spares. And so I got a full spare, but they couldn't get a matching one, as it turned out.
Apparently
but,
not. No.
Not only that, different nuts, so different sized nuts, different different problem. Anyway, I'm going to go out today and get that sorted.
I think you probably should make that a priority.
Yeah.
For the same reason as you, I also, when I got my car, it's now 5 years ago, got a full-size spare, which wasn't standard with it. And not only did you have to buy the full-size spare, you had to buy a new floor for the luggage area at the back.
Well, funny you should say that, because my luggage cover doesn't quite close.
No, that'll be right, because you've got a different
Which I find quite annoying, because every time you hit a bump, it goes boom,
yeah.
as it bounces up and down. Just sounds just like that. Yes.
Well,
first world problems.
Yes, indeed, that's right. Indeed they are, yes.
Okay, Fred, let's get down to business. And this first story is very exciting, and that is a NASA collaboration, the Solar Orbiter, which is focused on the sun, which we don't normally recommend, but these are specialised objects that look at the sun all the time. And they may have solved one of the great mysteries of the sun. This has probably got a lot of people talking.
I think so, yeah. So, considering it's our nearest star, there's a huge amount that we still don't know about the sun.
Yeah.
Really quite extraordinary. We now know, and this is something we didn't used to know, that the sun is highly magnetic, that it's sort of a tumultuous magnetic environment. That's what gives rise to sunspots, of course, and which are usually on the sun and not usually on the moon. The understanding of how this all works has been evolving, I guess, over the last 20 years, and in particular since spacecraft like the Solar Orbiter have been in action. Solar Orbiter is really an interesting spacecraft, because it sort of sits in the plane of the planets. As you might expect, it orbits the sun, so it's always looking at the sun's equator, and doesn't normally look at the polar regions of the sun, because you're looking at a very shallow angle if you do that.
Yes.
However, that is what these observations are reporting, made by principally European scientists, because it's an ESA-NASA project. And what's happened is that when they look in real detail, and not just in visible light, but in extreme ultraviolet light, so this is it's almost X-rays, it's so short wavelength. bearing in mind that sort of normal green daylight has a wavelength of 500 nanometers, these observations are made at a wavelength of 17.3, I think, nanometers, way down in the high energy region of the spectrum. Sorry, 17.4 nanometers, really high energy, tiny wavelength radiation. So this is what we call extreme ultraviolet. And there is a device on board Solar Orbiter called the Extreme Ultraviolet Imager, or EUI, and that takes pictures with an extreme ultraviolet filter. So the work that was done that's being reported dates from actually March last year, and it's an analysis, a detailed analysis of images of what's called a coronal hole in the sun's near the sun's south pole, and a coronal hole is a hole in the corona. What's the corona? The corona is the sun's the sun's inner atmosphere, if I can put it that way. The three main parts of the sun's disk, as observed by by normal astronomers for a long time, are the photosphere, which is the bit that we can see, that's the bright bit, the chromosphere, which is the sort of middle part of the atmosphere, and is actually, if I remember rightly, it's cooler than the photosphere. It's all a bit wonky in terms of temperatures. And then the corona itself, which is the outer atmosphere of the sun. So these coronal holes are sort of gaps in the inner part of the corona, where you can see a little bit further down into the chromosphere. And that's what these observations are about. What the scientists have done, have detected tiny, and by tiny I mean on the scale of the sun, tiny jets of material sort of squirting out from effectively the sun's surface, the photosphere, lasting of order a minute, between 20 and 100 seconds, and spurting out at 100 kilometers per second. So that's pretty high energy stuff. They're very fast.
Yeah.
And the thinking is that what we're seeing here is our first real hint as to how the solar wind is sort of ejected from the sun's surface, because this is the first time that something like this has been seen. I think these jets appear and disappear sort of all over the place, and with this very high speed. So this could be the holy grail, the missing link, if I can put it that way, in our understanding of how the sun works, courtesy of a spacecraft that's got incredible sensitivity in the extreme ultraviolet. The details that are being revealed here are quite extraordinary.
And now, you said the observations were taken in March 2022. Why has it taken 18 months for them to make the announcement?
That's pretty typical of research. Yeah, if you've got something that is an observation that needs a lot of what we call data reduction, where you're actually, turning the raw numbers that come from the spacecraft into things like images, and in particular velocities, because you have to calibrate the images to work out what sort of velocities these things are squirting out at. So I think the detail that we've seen here takes a long time to tease out, and hence the length of time that you've got to wait for the results. I think just one other thing that I mentioned. I said that the spacecraft is indeed looking at the sun's equator, but that's not permanent, because the spacecraft is in an orbit that will actually tilt eventually. And so I think in a few years we'll be seeing directly down onto the polar regions of the sun. And that probably means that we'll get a much better view of the bits of the solar disk that are being observed to find these jets. So I think this is a story that will evolve a little bit as time goes on.
So we still don't know a lot, like whether or not this is happening all over the disk of the sun, or only in parts of it, and I suppose the other thing is this happening all the time?
Yes, that's right. So all of those questions are ones that we hope will be answered. I guess an indication of the importance of this work comes from the journal in which it's published, which is Science, and Science is the leading American journal for really high impact scientific discoveries. So I think the fact that it's in Science tells us that there's a lot of excitement about this, and this is something that that maybe, as we're saying, it is the answer to the good old solar wind. That's where it comes from.
So will this work have to be peer reviewed, or is that already passed muster?
That's a good question. It is on. I think it's peer reviewed already.
Okay.
Looking at the reference that we've got there, so yes.
Now, like dark matter and dark energy, are solar winds incorrectly named, or is it actually wind?
It's they could have probably had a better name, but I think the reason why it's called a wind is because it's like wind on Earth, which is particles of air blowing around molecules of air. The solar wind is particles. It's subatomic particles, which are highly magnetized, highly electrically excited. It's a plasma that's blowing out. But nevertheless, it is a wind. You could call it a breeze, but that's a bit, something moving at 1 million kilometers an hour, you wouldn't normally call a breeze, I don't think. Maybe a solar gale might be better.
Yeah, that seems more appropriate. And these are the part of the reason we see aurorae, correct?
Yes, that's right. Yeah, the solar wind interacting with the Earth's magnetic, being spiraled into the Earth's magnetic field near the poles and interacting with the Earth's atmosphere.
It is a really exciting discovery, and I hope they do learn more about it, and we're able to, finally crack one of the great secrets of the sun, because it's the only opportunity we've got is to learn what our star is doing, because the other ones are all too far away to study at this level.
Exactly. This level of detail, really, you've got to be right next door to it, as the solar orbiter is. So we indeed are fortunate in having a view of a star that is a pretty normal star as well. It's not eccentric in many ways. It has gone through periods of eccentricity, as all stars do when they're evolving, but it's normal. It is very stable, and just as well it is, or else we'd be in big trouble.
Yes, indeed. Yeah, didn't someone classify it as a fairly boring star at some stage?
Well, that's what you need.
Nothing, amazing or extraordinary or weird about it. It's just, it's just, run of the mill star.
Typical might be better.
Typical? Yeah, that sounds nicer. I don't want to make it angry.
No, don't do
No.
that.
So, all right. So the story in a nutshell is that they think they've observed these fissures or holes in the inner outer area that's spitting out plasma at high speed. That is probably the cause of solar winds.
Perfect summary, Andrew.
I thought it was brilliantly worded too. Yes, indeed. Okay, and if you do want to look into that story, go to phys.org. They have a really good explanation of the whole thing. But it does appear that one of the great mysteries of our sun has finally been cracked. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Yes, indeed, and good to have your company. Fred, let's move on to our next topic, and it's all about spots. And spots seem to be a fairly common thing in our solar system. We have spots on Jupiter. We have spots on the sun. Boom, boom. And we've now
teenagers as well.
Sorry?
Spots on teenagers too. So yes, they're all over the place.
They are everywhere. And this is about spots on Neptune.
Yeah, that's right. So you're absolutely right. I mean, the particular kinds of spots that we're talking about are the ones in the atmospheres of gas giant planets, and all of the gas giants have spots from time to time. I guess the best known one and certainly the most aptly named one is the Great Red Spot on Jupiter, which is big and red, and it's a spot. And that's just to the south of the planet's equator. It's in one of the cloud belts, I think one of the equatorial region cloud belts, but south of the equator. We think that spot has been observed since Giovanni Cassini spotted it in sorry,
Dad jokes.
1665. So it's been around for a long time. A very long-lived feature. It comes and goes a little bit. It never disappears because you can always see its outline, even though the colouring sometimes changes. Sometimes it gets very pale.
Because I think we did a story some time back about the fact that it was starting to shrink, diminish.
That's right, yeah. But it's still there. After not far off 400 years, sort of getting on for that. So yes, a long established storm, because that's what it is. It's actually a cyclonic storm. I beg your pardon, an anticyclonic storm. It's a high pressure region, but it's still causing stormy weather in the region around it. If you can find it, and it's pretty easy to find, there's footage which I think actually goes back to the old Voyager or maybe even Pioneer days.
Yeah, I remember that.
Movie footage that shows the way the atmospheric turbulence, the atmospheric eddies move around the Great Red Spot. You can see circulation around it, so that it is, the air in it or the gas in it is circulating. So it's always worth following up on the Great Red Spot. It's such a interesting place. Saturn too has spots, more temporary. I think we've talked about Trevor Barry before, one of the great observers of Saturn spots, an Australian former miner in Broken Hill.
That's right.
Just recently won, last year and this year has won two very prestigious awards for his work on the spots on Saturn, which took him into the bosom of NASA planetary scientists because he collaborated with them for the Cassini spacecraft mission between 2004 and 2017. So a very worthwhile spotter of spots. Sorry, I can't get away from this, can I?
You can't. Yeah.
But they're just moving on, cutting to the chase here. The two ice giants, Uranus and Neptune, called ice giants because of the presence of ices in their atmosphere, mostly water, ammonia, and methane ices. They are spotty as well, but Uranus is less spotty than Neptune. And I'm not sure if we know why that is. But Neptune is definitely spottier. It was visited, and I think we've talked about this before, only once by a spacecraft, and that was Voyager 2 back in 1989. At the end of its grand tour of the giant planets, it flew by Neptune and showed a big spot on the planets in the planet's southern hemisphere. Unlike the red spot, it was a dark one. So it was called the Great Dark Spot. And it actually, but the interesting thing is that when that was followed up by the Hubble Space Telescope, it was found to have disappeared. Another dark spots have come and gone. So they're much more temporary in the atmosphere of Neptune than they are in the atmosphere of Jupiter. So we now have new observations which are of Neptune's spotty phase. And again, it's a dark spot. Now, this is a bit of history making because it's the first time spots on Neptune have been observed from a ground-based telescope.
Yeah.
They were made by the European Southern Observatory's very large telescope, the VLT, on Cerro Paranal in northern Chile. The telescopes which Australian astronomers have access to now, courtesy of a strategic partnership brokered by the Australian government back in 2017. So these are telescopes that are used by Australian astronomers, but this work actually doesn't come from Australian astronomers. I think it's UK and USA, if I remember rightly. What they've done, and this is why it's interesting to use a ground-based telescope, because you can use very sophisticated instrumentation. With the Hubble, you kind of stuck with what was put on it when it was launched, and there are some very specific, sophisticated instruments on board the Hubble, but you can do much better with a ground-based telescope. And in particular, there's an instrument called MUSE. Can't remember what MUSE is an acronym for. Oh, Spectroscopic Explorer, probably at the end. Multi-unit, I think that's what it is. Multi-unit Spectroscopic Explorer, which is a device that lets you look at the spectrum, not just of a single object, but of an area of an image. So you get what's called a data cube. You get a picture, but you get that same picture at every different wavelength. So it's sort of three-dimensional. And the work that's been done with MUSE on Neptune has revealed a dark spot, which is giving up its secrets because of the sophistication of the instrument that's being used, because you can actually deduce how deep it is in the atmosphere. It is quite deep, but it's not just a hole in Neptune's outer cloud layer, which I think for a while people have thought that's what these dark spots were. Holes in the outer cloud layer that's letting you see darker layers below. But actually, it seems to be more to do with a natural darkness of that area of the cloud sublayer. So the outer layer of that you see of Neptune, the top of the cloud deck, what you're seeing is particles of haze. These are probably ice particles and other particles. But the thinking as to what causes this darkness is a mixture of some of the ices with different hazes that has turned it darker, if I can put it that way.
Okay.
So it's all about planetary chemistry rather than holes in atmosphere in clouds. It's about chemistry. That's the bottom line. But there is another discovery that's associated with this that's got the scientists very excited. And I'm not a spot specialist on Neptune by any means, but they're very excited to find a bright spot nearby, which has also been identified as being quite deep in the atmosphere and not a sort of phenomenon of the outer cloud layer of Neptune. So that's been given a name. It's been called a deep, bright cloud. But I don't think they've yet worked out what's causing it. I think it's a bit of a mystery, that. So there is much still to be discovered. But I think, and certainly the ESO press release that I read, what is being really touted here is the fact that it's a new way of observing Neptune by using ground-based equipment of extreme sensitivity. The resolution of the Very Large Telescope in terms of the amount of detail that it can see is quite extraordinary, and this is just a really nice example of that.
Do we think these are storms?
Yes, I guess they're caused, the thinking probably is that they are caused by some sort of storm-type disturbance in the atmosphere. Even though, the evidence is that this dark spot is actually, it's chemical. It's a chemical colouring of the lower atmosphere. That probably originates because of turbulence or disturbances in the atmosphere. Maybe another of these cyclones, long-lived cyclones, like we find on Jupiter. So I think there's still work to be done on that, Andrew. But stormy weather seems to be a common feature of today's episode of the podcast, as well as what goes on the outer planets.
Yes, the sun and the gas giants. They all seem to have very similar anatomy, don't they? When from the observation,
or the planets themselves.
Well, not so much the makeup of the planets, but the way they behave.
Yes, yeah, that's right. Certainly, the gas giants do, because we know we don't actually know for certain that there is a core at the centre of them, although we expect there to be. And in fact, in the case of all the gas giants, you might expect it to be metallic because they all have strong magnetic fields, particularly Jupiter. So there are common features in the way they're put together, and of course the reason why we've got gas giants out beyond, in the far depths of the solar system, comes about because of the fact that they're beyond the frost line. So when planets were being formed, they could accrete ices more rapidly than the inner planets could, and got bigger more quickly. And that's what happened.
Okay. Interesting stuff. I'm glad astronomers don't name streets, Fred. I mean, we've got the big red spot, we've got the big dark spot, we've got the big bright spot. I mean, if they name streets, it'd be long street, short street, medium length street, slightly curved street, big curved street.
Yeah.
I mean,
Uphill street.
Downhill street.
Downhill street. You're right.
Yeah.
You're absolutely right. We're rubbish at naming things.
Very large telescope.
Well, exactly. Wouldn't you think it would be, Il Grande Telescopio Galileo, because it's European?
Yes, of course.
Das große Telescope Josef Fraunhofer or something like that, but it's not.
Yeah.
It's the very large telescope.
Very large telescope, which also sounds like a kind of lunch, VLT.
Yes, it does.
And I must say it was very clever of you not to talk about the spots on Uranus. But have you seen someone about that?
I'm not even going to go there, Andrew.
I'm going to keep trying.
Well,
I'm going to keep trying.
I got into enough trouble with Why is Uranus Upside Down when it came out back in 2027.
It's a damn good book, though, and very clever title.
Yeah.
Banned in America, of course.
Of course,
No.
never made it in America. No.
All right. And again, if you want to chase up the story about the spots on Neptune, phys.org. phys.org is the website where you'll find that story. I'm sure it's on other publications as well. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, Fred, we've reached the end of the show, except for the last bit. We've got to do the last bit before the end of the show, and that's all about...
Yeah, it's better than doing it after the end of the show.
Yeah.
Well, yeah.
This is all about audience questions. I'm going to do some text questions today just to catch up because we haven't done any en masse for a while. This one comes from David. From the point of a photon, it is emitted and instantaneously absorbed regardless of the distance it travels, and the universe is expanding faster than the speed of light. If the photon has an unimpeded path towards the edge of the universe, what does the photon experience after emission? Would it essentially become stuck in time? I love the show. You guys are fantastic at presenting complicated material in a way that people can understand. Thank you for all that you do in educating and entertaining en masse. One side note, I am a huge fan of Vegemite.
Okay.
We found one. One.
That's good stuff, is Vegemite.
Talk about a big dark spot. Yeah. It can really stain your shirt, that stuff. Thanks, David. Yes, to the trials and tribulations of a journey of a photon.
Yeah, that's right. So there's a number of issues here. We don't know whether the universe has an edge or not. In fact, it may not have. It may be just infinite, or it may just be bendy in such a way that you always end up back where you started from if you try.
Yeah, that one hurts my brain.
Yeah,
that one.
Yeah. But yes, for a photon, time doesn't really exist because they're moving at the speed of light. So yes, it's instantaneous creation and whatever happens to it at the other end. I think if you've got a photon that's traveling through space and being stretched in its wavelength, so it's getting redshifted, when we think about the expansion of the universe being faster than the speed of light, what we're really talking about is 2 places in the universe whose separation is greater than the rate of separation is greater than the speed of light. What it means is that a photon emitted by point A will never get to point B because it's always going away faster than it. So the photon itself doesn't really understand that. It doesn't need to know that. All it needs to know is it's traveling because it still is through space. It's traveling through space. Space itself can expand at any speed. Things going through space can't go any faster than the speed of light. I don't know whether that answers David's question. It's a slightly waffly answer, but
yeah. Well, I suppose. Yeah. What does the photon experience after emission? So it doesn't experience time. So He
Yeah.
wonders if it's stuck in time. I suppose
Well,
yes.
yeah, that's right. Yes, I think it is. I think that's the way we normally think of photons.
Yeah. I wonder though, with a photon, I mean, they have a fairly short journey to hit us from the sun after the 200,000 years it takes for them to get out of there.
Yes, that's right.
What happens after they hit the planet? I mean, do they bounce off and go somewhere else, or do they get absorbed and that's the end of their life, which means they've been ripped off because they could have just missed us and gone on forever?
Well, that's right. That's the extraordinary thing, isn't it? The photons that we receive from the sun are just a tiny fraction of what the sun emits. Most of them head off into outer space and to some distant civilization, if such things exist, it will just look like a star. But yeah, it's about the photon being absorbed, and so sometimes it's re-emitted as well, which is why you get greenhouse effects. Sometimes you get photons photons of light are absorbed, re-emitted as infrared radiation, and with a greenhouse blanket, that infrared can't get out, so everything just gets warmer. When a photon of light hits a detector, whether it's on an astronomical telescope or in your camera, it basically clouts an atom of silicon, knocks off an electron, which is then detected by the circuitry that that reads the image off your sensor. But it's being absorbed, as you say, and actually that's the process that gets photons out from the center of the sun. It's not the same photon that started off and took 200,000 years to get out to the sun's disk. It's a continuous scattering effect where one photon hits a subatomic particle, probably, rather than an atom, and is re-emitted then as a different photon, and then clouts something else, is re-emitted again, and eventually it winds its way to the edge of the sun's disk, the edge of the sun's atmosphere, and we see it.
And it yells, "Freedom!" Oh, damn, there's Earth.
Yeah, 8.5 minutes later, it hits the Earth. That's right.
Yeah. So when a photon is dead, does it become something else, or is it just gone?
It's a packet of energy, and so the energy's been redistributed as something else.
Right, gotcha. Okay, makes sense.
Photons never die. That should be a T-shirt, shouldn't it?
Old photons never die; they just end up as spots on Uranus. No,
that's something else.
Keep trying.
Altogether.
Thank you, David.
As well.
You'll stay away from that one. Thank you, David. Mike is next. Hi, Space Nutters. The density of gas in the vacuum of space is his topic. We're always talking about and looking at gas clouds in space. So my question is, what is the density of gas in between the planets of the solar system? What is the density of gas in between stars in the galaxy? And what is the density of gas in between galaxies? Also, what is the density of gas in a typical nebula? I'm assuming the answer will be X number of atoms per cubic metre, with X being the smaller number. Regards, Mike. There's a lot of questions in there, but yes, I hope you take something for your gas, Mike. It might help.
So yeah, it's actually more than you might think. This is so look. The easiest thing to do is look it up on Wikipedia.
Yeah,
density of the interstellar medium, and that's I think this is the upper limit, where you could get. And I'm thinking now about giant molecular clouds. So that's kind of what Mike's asking about, the density in nebulae. And a figure here I've got of 1 trillion molecules per cubic meter.
Oh.
Now that sounds like a lot, but compared with the atmosphere on Earth, it's nothing. It's still very rarefied. But then if you've got some of the hot nebulae, where things are a bit more excitable. So I guess that will be a cold giant molecular cloud, will be 10 to 12 molecules per cubic meter. In a hot nebula, it's going to be much, much lower. And in fact, the figure I've got here is maybe even as low as 100 per cubic meter. Did I say square meter there? I meant cubic meter.
Okay.
Cubic meter. So that's a sort of upper and lower limits in a way. And I think, the density of space between the planets is probably higher because you've got dust. Let's just try and check that figure by putting interplanetary space. 5 particles per cubic centimeter. There you go.
Ah, there you are.
Yeah.
That's not much.
No, it's not. It's not. It's not much. Even when make it quick cubic meters, it's not much.
That's light on. Well, it's not light either. Okay. Does that cover everything? Density of a gas in a typical nebula. Did we cover that?
Yeah, that's what we were just talking about.
Right.
There, yeah. Different kinds of nebulae.
Yeah. See how much I listen. But yes, thank you, Mike. We've got one more text question before we finish up today, and this one comes from Yuri. This is a bit of a speculator. The 2 proposals for living on another planet include essentially an encapsulated environment on Mars or, wait for it, a floating city on Venus. There have been some indications in the past that there might be organic activity in Venus's atmosphere already. Some of us psychology fans are wondering about the possibility of using algae to reduce the concentration of CO2 in Venus's atmosphere. However, there are other, more tectonic, volcanic in nature factors to consider. When comparing this with the long-term self-contained oxygen production needs for Mars, I personally favour Venus, which idea do space nuts see working best? Aside from staying on Earth and fixing our own problems, I would have normally said Mars, but he's brought up an interesting point about a floating city.
Yeah. So can you just read that bit about the organics in Venus's atmosphere again, Andrew?
Yes, there have been some indications in the past that there might be organic activity in Venus's atmosphere already.
Yeah. I haven't got this in front of me. There was a bit there where you said psychology. Did you say fans of psychology?
Oh, yeah, I don't think that's the word. Some of us... Is it phycology?
Yeah, it could be. Yeah. All
right. Phycology. Sorry, my brain just automatically interpreted an S.
The interesting ideas here, and whether you could make. So we think that the upper layers of Venus's atmosphere are relatively benign compared with the surface, which is a hellhole, as somebody once described it, hiding spring when it had rained on him for many, many weeks. It's not a good place. 50 degrees Celsius, and really probably lots of noxious gases as well from possibly tectonic activity. We really don't know whether that's happening or not. Different ideas come out nearly every week. But in the atmosphere, there are regions where certainly the temperature is much more akin to what we have on Earth. I would worry about the sulfuric acid drizzle, but I think that's only at certain layers in the atmosphere. So organic chemistry, I guess, may be taking place. So I'm trying to remember that there was phosphine was thought to have been observed by scientists at the James Clerk Maxwell microwave telescope in Hawaii a few years ago, and that was very exciting because phosphine in rocky planets would have to be produced by living organisms, or most likely would be.
And the popular press really latched onto that.
They did. They took it to heart. But then new observations suggested that actually, I can't remember what it was. I think it might have been sulfur dioxide. It was something like that was not a biomarker, but has a very similar spectral signature to phosphine. So I think there's still research being done on that kind of organic activity within the atmosphere of Venus. Now, my bet, and I don't know whether you'd agree with me, I suspect you would, Andrew, is I'd rather be in a controlled atmosphere on Mars than subject to the vagaries of what might be going on with atmospheric chemistry on Venus.
Yeah, I think so too. I think they're both fraught with danger.
Yeah.
Because you're in hostile, inhuman parts of the solar system where we're not designed to live. So you're always subject to catastrophe.
Yes.
Or the potential for catastrophe. So, but I think Mars would be a much more stable and much more controllable place to be.
Yes.
Perhaps.
Well, that's right. That's right. We know that Mars is essentially geologically dead. Some people think that the methane bursts that we see on Mars may be due to residual volcanic activity down deep below the surface. But I'd much rather have that than hanging around Venus. And of course, one of the other hazards on Venus is you're much closer to the sun. So the solar wind is going to be much more of a tempest than a breeze. That's likely, I think, to be one of the difficulties with any kind of human habitation of Venus. I suspect most scientists wrote Venus off a long time ago as a potential place to take humans. But it's nice to see Yuri still thinking outside the box and wondering whether we could do something in the atmosphere.
Yeah. And I've checked up on it because I needed to double check myself. Phycology is scientific study of algae.
There you go.
Yeah. It's a branch of biology.
More sense than psychology.
Yeah, my brain just went there. Which, it's one of my great failings. If I don't understand a word, I'll replace it.
Well, you could have thought. No, you could be forgiven. You could have thought, oh, that's obviously a typo.
Well, that's probably how it went. Yeah, indeed.
And it is.
Thanks, Yuri. Interesting argument, but I'm still voting for Mars.
Yeah.
But I'll send you a note.
Yes.
All right. We're just about done. I don't do this very often, but I thought I'd give a plug to our sister podcasts, Astronomy Daily with Tim and Steve and Spacetime with Stuart Gary. If you like the astronomy world and want to hear more on your podcasting platforms, have a listen to Astronomy Daily with Steve and Tim. They do a great job alongside Hallie, the effervescent artificial intelligence that we use, and Spacetime with Stuart Gary, as always, is very informative and really nuts out some of the big stories in day-to-day astronomy life. So, definitely worth chasing up those two podcasts, part of the Bytes.com stable. And don't forget, if you have a question for us or anything along those lines, jump on our website and send it to us, text or audio style, spacenutspodcast.com or spacenuts.io. Nearly forgot what the letters of the alphabet were there. But yeah, it's worth doing, and have a look around while you're there. Maybe consider going to the shop and buying Why is Uranus Upside Down and Why has it got spots? Ask a proctologist, or you can become a patron. That's an option as well. You can read all about it on our website. Fred, always a pleasure. Thank you so much. We'll catch you on the next episode.
It sounds good, Andrew. Take care, and we'll see you soon.
Okie dokie. Catch you then. Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio for getting an eye injection. I wouldn't wish it on anyone else. Hugh, thanks so much. No, seriously. And from me, Andrew Dunkley, thanks so much for your company. Looking forward to catching you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.